Включаемся мы? Да.
Все, мы... Михайлович, ну тогда, наверное, начинаем, да?
Что? Да, начинаем?
Ну, начинаем тогда, да?
Да, начинаем, давайте.
Ну, там как?
Да-да-да.
Let's start. Okay. The working language is English. Начинаем тогда, да?
Да-да-да.
Okay, dear colleagues, we're happy to start the School for Young Scientists, Pollutant and Sediment Mobility in River System, monitoring studies to identify human impacts. And the first introduction words will be done by the organizing committee chair, academician Nikolai Kasimov.
Спасибо, Сергей. Добрый вечер, добрый день, дорогие друзья. Я знаю, что эта школа вызвала большой интерес. По-моему, собралось более 350, по крайней мере, заявилось 350 участников. И ее мы проводим в рамках довольно большого проекта по разработке технологий комплексного интегрального анализа городских территорий на примере мегасити московского, агломерации московского региона, который посвящен изучению в основном микрочастиц в различных средах, начиная от аэрозолей, атмосферной осадки, дорожная пыль, почвы и водные потоки. И вот сегодня мы хотели сосредоточиться на водных потоках, изучение на особенностях миграции поллютантов в водных средах, водных потоков, поверхностных водах. Ну и мне кажется, что эта тема чрезвычайно актуальна, особенно для России, где она могла бы способствовать проведению, подчеркиваю, более правильного гидрологического, гидрохимического или, как мы сейчас больше любим говорить, гидрогеохимического мониторинга водной среды. Поэтому я желаю всем участникам хорошей встречи, здесь нас очень много, хорошей встречи, послушаем лекции, поработаем. Ну, я думаю, что это послужит в том числе толчком к нашему дальнейшему научному сотрудничеству. Всего доброго, желаю успехов.
Сергей, let me start our first session. I would like to thank the organizing committee. I'm happy to be the first convener of this school. And I wish the fruitful work for everybody, good presentations for lecturers, and new brilliant ideas for young scientists, and the final stage of this school. I hope all technical problems will be solved and we have no technical problems. So let's start now, and I would like to give the first talk to Mr. Björn Helm. He started hydrology and water management at Technical University of Dresden. Presently, he is the head of the Urban Hydrology Research Group, and his research interests include water management planning on catchment scale, impact assessment of urban systems on water resources, monitoring and hydrometry of urban water systems, quality, quantity, etc. Mr. Helm, please begin. So I will follow the time, and yeah, you have 45 minutes, and then we have quarter of an hour for the questions.
All right. Do you see the screen now? Do you have the full screen of my presentation?
Yes, yes, we see.
Okay. And do you also see the laser pointer?
Yeah.
Okay, so I'm going to start. So thank you for the invitation and for the great opportunity to give this talk to you and to your young scientists. And I hope I can transfer some of our approaches and knowledge to you and inspire a bit the perspective of urban rivers to the geographers. So the first slide may surprise you a bit. I took the freedom to show your university because what I want to point out is that most of the rivers we see most of the time are urban rivers. If you go to the university every day and if you are in one of the upper floors, you probably see the river every day. But despite this fact that we experience urban rivers every day, they are very much charged and they are burdened by several pressures. So achieving environmental and ecological goals is especially important for those urban rivers because we appreciate them a lot of time, but it's also very challenging because the urban environment causes a lot of stress to the rivers. I want to point out some of those pressures that we experience in urban rivers. So first, there's channelization. That means we have typically in urban surroundings a straight course of the river and few structures within the river because the rivers, especially in the 20th century, were designed to flow quickly through the cities and to prevent flooding. And it was not that much emphasized to have a nice surrounding. So the picture you see here is Los Angeles River in California. It's one of the most drastic examples of urban channelization projects. And in the last 10 years, there were billions and billions spent to rehabilitate this very unnatural type of river. On the second scale, so in the direct surrounding of the river, we have the riparian zone that typically shows a lot of unnatural structures. So also, this is also nicely exhibited in this picture. So here's a train station right next to the river. And very often we find roads or other types of infrastructure aligned with the river because in historic times it was quite challenging to cross a river. So the river was a barrier that was bordered but not crossed or crossed as few times as possible. As a consequence of this intense use of the riparian zone, we have a lack of shading in these areas. So we don't have a lot of natural vegetation, and that causes thermal stress. We have heating of the river, and we have, again, we may have also a direct input of contaminants from those riparian zones. Even one scale further, if we look at the entire catchment of the urban area, we see that the changes in the catchment due to the settlement activities lead to further stress for the river. We have vast impervious areas, and during rainfall times, the water quickly flows away from those areas, increasing the peak flow in the river and increasing the hydraulic stress in the river. But on the other hand, the water that ran away quickly is not infiltrating into the ground, and we have a lack of groundwater recharge, and due to that, decreased low flow during dry times. Other impacts of the catchment area are the urban heat effect. So urban areas typically have higher temperatures, and these higher temperatures also transfer to the river itself. So apart from the lack of shading, we also experience a local climate around the river that further increases water thermal stress. And obviously, as we are very active in our urban areas, we have industry, we have commercial areas, we have our own activities. We also have a lot of polluting activities. And finally, due to our water usage and the discharge of the wastewater, we apply physical hydraulic stress to the river, and we also import pollutants into the river. And this may be at very short instances. For example, during storm events, we have high hydraulic pressures and also high chemical pressures on the river. And you see one example how that might occur in the lower picture here. That's a combined sewer overflow from the city of Dresden during a rain event. So the discharge here into our river Elbe is about as much as a small creek, and it occurs only very short periods in time, but it carries a lot of pollutants that must be managed appropriately. In the last 30 years, an increased awareness arose around this, the problems that those discharges cause within the river, and a group of pollutants that is especially relevant in this context are the urban sediments and their attached pollutants. So today I want to focus on, in my presentation, on particle-bound pollution from urban areas, and want to share some of our research activities and some general concepts, how those pollution types occur, what they mean, and how they are managed. My name is, as I was nicely introduced by Michael, Björn Helm, and I want to start my presentation with some key questions. So first of all, I've given you a rough idea, but I want to further define what are urban sediments, what are they composed of, and how do they behave. As a result of this, I want to answer the question, are urban sediments a problem? How are those sediments assessed? So how can we determine their amounts and critical zones where they occur? And finally, how can impacts of those sediments be mitigated? Before I'm going to dig into the topic, I was told that you are mostly young scientists from the field of geography, so you might have not been in touch so much with the urban water cycle. So I want to give you a very brief introduction how the urban water cycle is managed, so you understand the terms I'm using in my presentation. In principle, we have two types of drainage systems in urban areas. On the left-hand side, you see a separate system in which the sanitary sewer, that is the wastewater that's coming from households and from the industry, is collected in a separate sanitary sewer system. It is transported to the wastewater treatment plant where it is treated, and then the treated water is discharged to the river. During storm periods, we have wet weather discharges, and they are conveyed by the stormwater system. That's a separate sewer. That's why it's called a separate sewer system. And this water is typically discharged to the river directly and without further treatment. On the other hand, we have the combined sewer system that you can see here on the right-hand side. In this system, we have a different approach. We just have one type of sewer network that collects both the domestic sewer or the sanitary sewer and also the stormwater. This combined sewer system is dimensioned in the way that the majority of the flow is transported to the treatment plant and then treated and discharged to the river. But especially during high flow events, the system might be overcharged and there might be overflow occasions. So times when we discharge this combined sewer, the mixture between stormwater and domestic wastewater directly into the river. And with this in mind, I want to introduce where our urban sediment sources are located and how they generate pollution. So as I've already pointed out in one of the previous slides, urban areas are characterized by a high level of different human activities. We have industrial areas, we have domestic areas, we have roads with a lot of traffic. And all those areas also contribute to particulate pollutants. So for example, in industrial areas, we might have production processes that emit certain types of particles or certain types of pollutants. Furthermore, we have combustion processes. Those might be, again, industrial combustion processes to process substances, for example, to produce cement. Those might be also thermal or power plants, but we have also combustion processes in traffic and in private households. So all the time you're starting your chimney at home, if you have one, you're starting a combustion process that emits particles to your environment. So apart from those combustion processes, we might have also construction sites where we have a more typical type of erosion that you may know from natural areas where dirt is loosened and washed off from the surfaces. But we may also find particles from different types of abrasion. So in traffic, we find abrasion from the car, from the road surface. So the tires of the car apply friction to the road surface, and this takes off some of the material of the road. It also takes off some of the material from the tires. And at each process, at each instance, when you brake your car, you also apply abrasion to your brake pads, and they are slowly eroded away. So we have different types of, furthermore, we have different types of surface materials. We have surface coatings on the buildings to prevent algae and fungi from growing on those surfaces. We may have metal roofs that are also oxidizing throughout the time and emitting heavy metals. And all different types of coatings and materials on the surfaces of our area. In addition, we can also notice mismanaged waste. So waste just placed in the area is also often washed away and drained away by the sewer system. And finally, especially in the combined system, we may have the impact of municipal wastewater or sanitary wastewater that has a complete different set of pollutions. All those pollutants that are generated in urban areas are then transported either through atmospheric deposition. So we have the emission, and then the sediments or the particles are transported by the wind force through the air. We might have a wet deposition of those particles then during a rain event. So suspended particles in the air are washed down by rain event, and we might have wash off from facades and from road surfaces. And all those waters that fall in the city, they drain into the sewer system, where they are transported towards the river, as I've just explained in the previous slide. In the next step, I want to answer the question: what are what are the properties of those sediments, and I want to give you an insight to this based on 11 samples that we've taken from one of the sampling sites that we have in our monitoring system here in Dresden. It's 11 samples from a storm sewer system, so one of the systems I've just introduced. And they were taken during 11 storm events. And I want to point out to some very typical properties of urban sediments based on those samples. So first, there's several abbreviations here. So we have fine and coarse sediments that are abbreviated with F and C, and we have organic and inorganic sediments. And then I use SS, suspended solids, as a abbreviation for the sediments. So for example, FOSS, as you see it up here, is the fine organic suspended sediments. So what is very apparent when looking at the two fractions of the fine sediments is that urban sediments are predominantly fine sediments. That is, they have a grain size of smaller than 63 micrometers. So in a natural system, they would correspond predominantly to the clay fraction. But in contrast to clay, they have a quite low cohesive strength. So those urban sediments, they don't attach very well to each other, but they are very loose and behave more like dust and loose dust. As a consequence of both of these properties, they are very easily mobilized. That means that low shear force from runoff or low wind shear force from wind action moves those sediments around, and they accumulate in surfaces and areas where they are deposited. A second property I want to stress out based on this figure is that a lot of those sediments have a high content in organic substances. So we evaluate the organic substances by loss of ignition at 450 degrees. And we see that between 30 and up to 90% of the sediments are composed of those fine organic substances. As a result of both the fine particle size and the high organic content, we have a very big active surface on our sediments, and as a result, they have a quite high pollution potential. So particulate pollutions that have the tendency to absorb, easily attach to those particles and are transported with those particles. That leads us to the different types of pollution that we might find in such urban sediment particles. So we have typically indicator substances that we can use for identifying the origin of a sediment. So for example, for the different types of road traffic sediments, from tire wear, from brake wear, or also from road abrasion, are often characterized by high contents of heavy metals and polyaromatic hydrocarbons. Both of these substances are of special concern because they are cancerogenic, and they hardly degrade in the environment. So they accumulate over a long time in systems where they attach. One thing that you can do is you can identify the property of those particles individually, and you can also fingerprint their composition by chemical analysis. In this figure, you see an example of scanning of road sediment particles with electron microscopy, and the determination of the elemental content of the different types of particles. So you see quite distinct fingerprints on the different element contents that you see here. So for example, one is a part of a road abrasion that is characterized by quite high components of several elements, as in contrast to the more brightly depicted types of sediment that you see here, that are characterized by lower contents of certain elements. But for example, with kalium, they also with potassium, they all show quite high concentrations. When looking at the combustion processes, so processes of burning substances, we find a different pattern that is mainly dominated by polyaromatic hydrocarbons and organic matter. Polyaromatic hydrocarbons are a substance that is really of special interest in the recent years because it is identified more and more as an ecological burden to our environment. So in the EU regulation, we have 17 types of polyaromatic hydrocarbons that are characterized. And this is a study by my former colleague, Jin, who sampled sediments in our city in Dresden and did a fingerprinting profile of different sources of those polyaromatic hydrocarbons based on their composition. So you see that according to the composition of the polyaromatic hydrocarbons, you can determine whether you have gasoline contribution or surface pavement, diesel or industrial boilers as an origin of those polyaromatic hydrocarbons. As other examples, for example, for surface materials that are used for coating, we frequently find heavy metals, especially based originating from metal roofing. We may find herbicides or microplastics based on the type of surface that they stem from. And finally, we have wastewater as a major source of pollution with a very distinct type of fingerprint. So in wastewater sediments, we find industrial chemicals from the industrial wastewater. We find pharmaceuticals or their residuals from domestic wastewater, but we also find very high contents of organic matter, nutrients, and microplastics. So we have quite a bunch of substances that are quite unique to urban sediments and that each cause individual threats to the ecosystem. So I want to introduce some of the ecological effects that urban sediments may have in the river. So as I've pointed out, those sediments are mainly distributed in the fine particle size fraction. So what happens when they enter into the river is that they change the substrate composition, and especially they enter into the pore space of the substrate, and they block this pore space for other species. So the upper example here shows how salmon and trout are using the spaces in between core sediments throughout their life cycle. So especially the eggs and the larvae of those fish species depend on having free pore spaces in the sediment. And if our pollutant charged fine sediment enters the river and clogs those pores, basically those fish species cannot survive. As I've pointed out, those sediments are also high in their organic matter content, and as a result, they cause oxygen depletion. They are oxidized in the river, and the oxygen is taken out of the water column or out of the pore water in the sediment, in the natural sediment, and as a result, we see low oxygen concentrations in the water body and especially in the riverbed. That also creates hostile environments for those species. I already pointed out in the previous slide that most of those substances have acute or chronic toxicity effects. That means they may harm the species directly by poisoning them, depending on the duration of the application. And last but not least, those sediments being deposited in the river and accumulating in the river lead to habitat alterations. So the lower picture here shows how one of our rivers that we monitor intensely is dredged because too much sediment has accumulated throughout the time. So I hope with those 2 slides I could answer my first 2 questions. And with that, I want to show you some of our research on assessment of the road deposited urban sediments. One of our assessments was specifically focused on road deposited sediments. That is sediments that are emitted either from traffic or placed on traffic areas. So what we've done in order to assess those sediments is we've used an emission inventory model, the EMAP model, that is widely applied in the EU for accounting for emission amounts. And we've coupled this model with a traffic propagation model for the whole street network of our city of Dresden. And what you see in the figure on the left-hand side are the roads in the different color scales, and those color scales apply according to the emission amount on those different types of roads. So we see that we have a lot of green roads with a low emission potential. Mostly those are secondary roads that don't have a lot of traffic, and as a result don't have a lot of emissions per day. So the emissions are stated in milligrams per square meter in day. And what we also could do based on this emission model is we could identify hotspots of emission, and we could also classify the roads according to their emission intensity. And what we see in this histogram is that a lot of the roads have rather low emission intensities, and there's only few roads that show those rather high emission intensities. And now if we look into the different sources of those road deposited sediments, we have the three main sources of sediments that are tire abrasion, so wear off from the tires that contains to a high content of total organic carbon, but also rather high values levels of polyaromatic hydrocarbons and different types of heavy metals that come from the tire production process. Furthermore, we have the brake abrasion with another quite unique fingerprint of pollution, and we have road abrasion. We've seen that brake abrasion contributed to a much lower extent to the sediments, but on the other hand, it also shows the highest values in those heavy metal concentrations. So if we plot the total emissions against the type of emissions, we see that brakes overall have the lowest contribution, but not as little as would have been suggested by their little amount of contribution, but this is compensated to some extent by the higher concentrations in the contribution. Now, if we plot the types of emissions against the total length of the road, we can confirm this impression that a small fraction of the roads, about 20%, contribute about 60% of the emissions. That means if we want to apply sediment mitigation strategies of road deposited sediments, we should focus on those 20% because they contribute most of the emissions and they can be managed most effectively. Now, this emission model was a motivation for us to also look into a validation experiment, and for this we initiated a road deposited sediment sampling campaign. So a couple of our colleagues and a lot of our students went to the road and vacuum cleaned the roads with a wet vacuum cleaner in order to detach the sediments from the road surfaces and to collect those sediments that are deposited on the road surface. And they've developed the monitoring strategy according to traffic density. So here we have the same color scheme as in the road map before. We see quite different road traffic intensities, and they were sampled systematically throughout our city. Now, very contrary to what we've expected, we found consistently the highest deposition levels on roads of the lower intensity classes. But let me first introduce this figure a bit more in detail. So in the different colors of the columns, you see the different sediment, the particle sizes. The columns that are grouped together represent different amounts of dry weather days before sampling. So we have 4 columns and they represent 1, 3, 7, or 10 antecedent dry weather days. And the numbers above the columns determine the numbers of days that after the last street sweeping event. So in Dresden, we have a dynamic street sweeping calendar. Every road is cleaned with its own frequency. And this is an important boundary condition when conducting those sampling experiments. So what we see as general tendencies from this figure is that we have most of the sediments overall on the low density or low intensity roads. And we confirm a pattern that with increasing antecedent dry days, that means with longer periods of without rainfall, we have an increasing amount of sediments on our surface. Now, we were thinking very hard why our sampling results did not match with the sampled results, and we came up with the solution that emission of those road deposited sediments works quite differently from the deposition. That means the places where those sediments are emitted are not the same places where they are also deposited. In order to improve this model, we extended it by including a deposition module to the emission model that is briefly described here. So the load of road deposited sediments that we obtained from the sampling was corrected by several scaling factors, including a factor that accounts for coverage in the surrounding of the sediments, slope of the road, and traffic intensity, and also from major wind exposition in the dry weather time before. And further, we use scaling factors to adapt or to optimize the fit between measured samples and modeled samples. These small adaptations to the emission model largely improve the prediction of deposition characteristics. So on the in this plot on the right-hand side, you see the fit before with the emission model as colored dots, where you see that you have hardly a match. The model particle loads behave very differently from the measured particle loads, but with this extension of the model, we could fit them quite well, or we could achieve quite a good agreement between modeled and measured sediment loads. So this was one of our examples on how to assess the road deposited sediments deposition. But once we have a better understanding of where we find those sediments on the surface of our urban area, we also want to understand how they are transported through our water system and into our river. In the last 7 years, we have implemented an extensive monitoring system throughout the city of Dresden, with a special focus on a creek, Lockwitzbach, that enters from a rural background into the urban area, and that is very interesting for us to assess the impact of the urban area in an integrated way. So we have 7 measurement stations distributed throughout the town, where we measure water quality, water quantity in the river, but also in the urban water system. So we have several two monitoring stations in the river and several monitoring stations in the urban wastewater system. I want to direct your attention especially to this measurement station number 5 that is dedicated to a separate system. We are going to look into the results of this system more in detail a bit later. So as I've mentioned, I want to focus on monitoring of total suspended solids or on sediments, and for this we use 2 principal monitoring techniques. They are both based on the photometric measurement principle. One is by absorbance measurement with the spectralizer. The principle is shown here. So we have the extinction of light through the passage through the water, and we detect the amount of light that still arrives at the detector. And the other measurement principle is the scattered light transmission that is represented here, where we measure the amount of light that is scattered by the particles to a detector that is placed at 90 degrees angle from the light emission source. So both principles based on optical measurements, but have different aspects to focus on. As an overall result of our analysis so far, we can state that those sensors can work quite well in determining the TSS concentrations in the system, but they typically require a system or site-specific calibration. That means I need samples from site in order to scale their measurements to my site-specific conditions. So as you can imagine, depending on the type of particles that are transported and depending on their size distribution, this might vary quite a lot. I want to emphasize this insight with this figure that shows the in-house calibration of a sensor in this dashed line as compared to our local calibration that was obtained from local samples. So you see that we have a drastic underestimation of the sediment loads or of the TSS loads if we base our measurements solely on the global calibration. A further benefit of using local samples to analyze the TSS concentration is that we can obtain additional variables. So we can focus, for example, on the fine fraction that is especially mobile and especially prone to pollutant transport. We can also focus on the organic fractions or on the volatile fractions. And another advantage I want to point out is the explicit determination of uncertainty. So based on the quality of my regression equation, I can directly obtain the uncertainty of my sensor measurement. With this short introduction of the measurement principle, I want to focus on the area at measurement site 5 that I've briefly shown on the overview map. Here are some features of this area. It's as I've already mentioned, it's a separate sewer system that consists of in total 30 hectares of area with 18% of buildings, 25% traffic area, and about 60% vegetation area. We have 800 inhabitants in this system, and as counted from the dynamic roadmap, 7.8 million car kilometers per year. So quite a lot of driving in the area. We use those principles that I've just introduced of local regression between the sensor reading and the different sediment fractions in order to obtain regression equations that are locally adapted and that we can then use to predict event courses more in detail. So here you see the example of one such event course for fine inorganic sediments and how they are mobilized, especially during the beginning of a discharge event. And we also can show that with our prediction intervals, we quite conveniently match the sampled results. The same holds true for the organic fraction of the sediments. We see a lower total contribution of those organic sediments in this event, but we also reproduce quite well our sampling dynamics with the adapted measurement. So if I apply those locally adapted calibration coefficients to my long-term measurement time series, I can draw annual balances. So for example, in our area, we have a total emission of 1.6 tons of sediments per year. They come with a quite substantial fraction of uncertainty. We hope to further reduce this uncertainty with the increasing number of samples that we take into account when establishing our regression relationship. And we can also determine the fractions of sediments. So fine sediments distinguished between organic and inorganic fractions, as well as coarse sediments. So for a management approach, I can then locally optimized also focus on mitigation strategies that fit to this type of pollution. Based on this data source, we can also use hydrodynamic simulation models in order to describe the discharge patterns of our area and the emission of particle-bound pollutants in the area. So here are two quite early examples of this, where we used a hydrodynamic model that is calibrated based on the observed discharges. And then we used a regression model to describe, for example, polyaromatic hydrocarbons based on the pollutant dynamics that were determined with the turbidity sensor. And a similar example for zinc dynamics. This one is even including some locally sampled event characteristics, where we see that at least in this part of the event, we match quite well between the simulated and the lab results. So with those two approaches for sediment assessment in my area, I want to introduce the mitigation options, because I think I'm also getting short in time now. Reminding you of the urban water cycle that I've been introducing and the processes of wash-off and transport of particulate pollution, I can focus 3 scales of management in my area. So the first management option would be the management at the source. This could be I change my traffic management. I could impose lower traffic regulations or low traffic regulations in especially critical areas. I could adapt street sweeping plans in a way that they optimize the amount of urban sediments being collected. And I might impose combustion or emission regulations. This is a very big topic in Germany in the last years, especially the regulations for diesel cars are quite strict now, and they have to come with advanced filter technologies so they do not emit as much particulate pollution. On the second level, I have decentralized options for control. So I might use gully filters as you see here, that filter the runoff from the road before it enters into the sewer system, and it collects the sediment in those traps that are included in the gully. Another approach would be to not have the water flow into the sewer system at all, but to infiltrate the stormwater decentrally or in infiltration swales or on green areas, and attenuate the pollution by that. And finally, we have centralized control strategies. That would be, for example, a control system implemented in a sewer system where I can control not to emit the highly polluted proportions of the water, but to only allow for this combined sewer overflow during times with low pollution levels. Another option here would be retention and infiltration basins that provide filtration of already water that was already conveyed through the sewer system in a centralized place before discharging it into the water system. I want to end the examples with one of the mitigation options that we've looked into based on our study area. So we did an investigation on the sweeping efficiency of 2 different types of street sweeping machines. And we found that they do perform quite differently. So the city fund type of sweeping machine achieves rather high cleaning efficiencies as compared to the street sweeping efficiency of the Duelvo machine. So based on the different street sweeping efficiencies and different sweeping intervals, we can then predict the change in simulated TSS based on our sediment transport hydrodynamic model, and we can compare the impact of those management strategies finally. And I want to finish my talk with some conclusions. I hope I could show you that urban sediments are emitted from multiple sources. They are easily mobilized and have a high pollution potential. And due to this, they cause adverse effects on water quality, on habitats in the river, and also on the fluvial species, so on species living in the river. I hope I could show you that monitoring along with along the emission and transport path, allows us to identify hotspots in pollution in our area and to identify critical periods of pollution. So what are critical rain events and what are critical areas of increased pollution in order to manage them more efficiently. Mitigation strategies should be source specific. That means they should address those hotspots in emission, and they should aim at different spatial scales. So a combination of on-site, decentralized and centralized mitigation strategies is going to be most effective. With this conclusion, I want to end my talk and want to show my colleague Jakob, who is taking samples in a quite turbid river and under quite harsh conditions. So I don't recommend this to do it by yourself if you can avoid it, but it's also quite valuable because it provides us with the samples to do all the analysis that you've just seen. So I hope I could raise your interest, and I would be curious about your questions.
Thank you very much, Björn, for very interesting presentation. Let me see the questions. Yes, we've got a few questions, and let's start from the first one. Well, the question to begin the discussion is the following. Is it correct to call as sediments the particles laying on the roads? And what do you name as sediments then?
Yes, that's right. So it's probably from a geomorphologist point of view, it's not what you would consider sediments, but in their effect and in the way they are transported, we consider them as sediments. It's the emissions that are caused in an urban area and that are deposited on urban surfaces that we call urban sediments.
Mm-hmm. Thank you. Thank you. Because usually in Russia we call it the road dust or something like that.
Ah.
Okay, the second question is like this. Did you check different blowout sediments between e-cars and diesel or petrol cars?
No, we have not looked into this yet. The e-cars are too new yet, but I would expect that the tire abrasion, so the particles coming from the tires and from the brakes, they should not be very differently. And what would be different is are the types of sediments that are coming from the combustion, from the exhaust, because the electric cars don't have any exhaust anymore.
Mm-hmm. Thank you. The question from Artem Gorbarenko, hydrology department student. What fraction of sediments is the most dangerous for the environment?
That's a very general question, and it depends specifically on your conditions. So heavy metals might be a problem, especially if they are in a very available form, as they accumulate quite strongly in the species. So if you have a lot of heavy metal import from your sediments, those are certainly dangerous. But what we find most commonly as a problem is that oxygen depletion is caused by the organic content of the sediment. So especially in low-flowing rivers or in slow-flowing rivers, this is a major concern, that those sediments settle during low-flow times and that they use up all the oxygen that is dissolved in the water.
Mm-hmm. Thank you. The next question. There are a number of questions, and we have some new questions now. The question from Mikhail Makarov. How much more environmental friendly will the urban cycle become if renewable resources of energy will be used?
Yeah, again, it's certainly an interesting question that merits our study, but it's quite general to answer it, right? So we have still a lot of potential to improve our to reduce our footprint, to use more environmental friendly building materials, to to define traffic restrictions that are most helpful for saving our environment and also saving our health, because a lot of those pollutant types also affect our human health, not only the environment. So there's still a lot of potential, and I would say we cannot live without any footprint, but we can do much better than we do now.
Thank you. Next question is from Lewis Hill, recent geography graduate, University of Plymouth. The question is, do you have any plans to look at fine particulate pollution originating from airports, assuming this must have a large impact on river pollution?
Yeah, again, it's an interesting question. We only have a rather small regional airport at our town, so we would need to find, we would need to be paid for a study of this in another town, I guess, because it would be more interesting in Germany, in Frankfurt or in Munich or in Berlin. Berlin has the new airport now, finally, after a lot of years, so maybe that's a good starting point for such a study.
So one more question from the student of landscape geochemistry department of our faculty, Nikolai Sobolev. If you speak about heavy metals as particle-bound pollution, what can we say? Which role does the cadmium play? What can you say about cadmium?
Yeah, cadmium is quite a special type of heavy metal because we find it quite widely spread in Germany. So in contrast to other heavy metals, for example, zinc and copper and lead, they are very strongly related to traffic activities. And cadmium, in contrast, is much more widespread. And we assume that this comes basically or mostly from coal combustion, and that the coal particles are distributed quite widely throughout the area, and that's why we find them everywhere. So cadmium is much more toxic than other heavy metals, but also we find it at lower concentrations in Germany. But that very strongly depends on your regional boundary conditions, the specific composition of your urban sediments or of your road dust, as you call it.
Okay, thank you. The next question is from Josip Olson. From the Institute of Mineralogy, Geochemistry and Crystal Chemistry of Rare Elements in Moscow. First of all, great thanks for very interesting presentation. And the question is quite simple. Is there any chance to read an article on the topic of your presentation?
Yes, there are several. So we are currently working on an article that dedicates to the measurements in the sewer system. So this is not published yet. There are just some conference papers based on this. But especially the works by my colleague Jin Zhang, they are quite well published, based and that's the studies focusing on road deposited sediments and sampling on the urban surfaces. So there are several. If you write me an email, I think you can find me if you use my name from the program, and I can send you some of the articles.
Well, and I think this is the last one, and it begins from many thanks for your nice presentation from Zara Abdullahi, PhD in hydrology and sediment quality. And the question is the following. I would like to know if we could have your PowerPoint and also your related papers. It is similar. Yeah. Björn, thank you very much again from all the participants for the very interesting presentation and answers for the questions. And now we have about 5 minutes break before the next presentation of Dr. Sergei Chalov.
Thank you also for the opportunity of presenting our research.
Thank you, Bjorn, a lot that you accepted this invitation again.
So I'd like to suggest you to continue if everybody is ready. So let's start. I would like to present you Associate Professor of Department of Hydrology, Faculty of Geography of Lomonosov Moscow State University, Dr. Sergey Chalov. His research interests are focused on sediment quality and quantity, and remote sensing applications for sediment transport, fluvial processes, stream ecology, biodiversity, transboundary rivers research, etc. He is an expert on rivers of the Baikal, lake catchment of the Kamchatka Peninsula, and Arctic rivers. So, Sergey, please begin.
Thank you, Mikhail. Dear friends, dear colleagues, it's my pleasure to proceed with the second lecture in our School for Young Scientists, and we're happy as one of the co-organizers of this event. We're happy that it's got some interest from different research groups, and we see now in YouTube quite a good number of the participants. And actually, I would generally change the direction of the talk, and firstly speak about. So maybe I would go this way. I would mostly speak about the rivers which are not so urban as the previous speaker, as Bjorn said, but I would focus on more natural state, and I would explain why in the lecture, because as far as we're focusing in the school on the pollution problems, but the natural rivers are very important. But before I would speak about the research part of my presentation, I would briefly show again the photo for our university, which was also the first slide in the Bjorn on the previous speaker presentation. And here I would just mention that we are topographically the highest faculty of geography in the world, since we are quite large and comparable to other faculties of geography or institutes of geography abroad. You can see in the statistics which are on the slide that this is very big institute and big educational center. And this word large I would use for making a bridge to the topic of my presentation, to the large rivers. So we're working in the large university, in the large faculty of geography, and we are studying the largest rivers. And here in this talk, I would give 5 examples of the research related to largest rivers across Siberia. And the case studies are distributed over Yenisei, Lena, and Kolyma catchments. And these rivers, at least there are 3 of them, the Yenisei and Lena, which you can see on the slide. These rivers are typically called like Russian Arctic pillars, mean that they are standing up to push the Arctic Ocean. And so these pillars are the main focus of our interest. So that's to give you impression of the small urban creeks of Dr. Helm is the photo which is on the slide. This huge river with big this turbidity pathway on the confluence of 2 tributaries. And you can see this as a matter of scale, the huge bridge which crosses this river. And this is so-called Yuganskaya Ob. But the interesting thing that it is only a small part of the Ob River. So actually, if we proceed on this photo to here to the left, we will see the actually the real orb, which is almost 6 times larger. And this is the way why we are talking and use this terminology largest or large, as far as this huge water stream on the photo is just the 15% of the Ob River. And the challenges to talk about the large rivers when we especially focus on the pollution problems and on the issues related to, in some way, urban topics is the 3 points, which I would talk in the introduction of my presentation. The first is the role of sediments. And here I would not say a lot, and I even skipped a few slides while listening the previous speaker. As far as the role of sediments as a key pollutant drivers is rather obvious, and we are not like we would not talk about this in this lecture, but to provide enough evidences that we are interested in the looking into the large rivers sedimentation issues in relation to pollution problems, I would speak about a little bit about monitoring and about regional scope of this research. And the only thing related to the sedimentation as the key question in the hydrological or hydrogeochemical research, I would make a citation of rather famous papers which maybe give the best statement of the problem and or emphasize that the sediments are integral and dynamic part of aquatic systems, and the central role of it in the research, both from the ecological perspective, what's also Bjorn said before, and also from hydrological perspective. And that's why there is a big number of scientists looking on the sediments from different perspectives. And so there is also many ways now to combine together the hydrology and geochemistry in these questions. But here on the further slides, I would also comment the problem of sediment research from the points of the monitoring, and especially from the points of lack of the substantial monitoring efforts. And so if we would look on the problem of the sediment transport or sediment pollution, we will see that's the sedimentation itself is very fastly changing parameter and factor. But actually what we are having to learn about the sediments is very irregular measurements and very dense stations, very dense gauging stations. From the point of view of the impacts that sediments have on the river system, we would focus firstly on that it's the sediments are important source for heavy metals, nutrients, and other pollutants. That's mechanically they are impair ecosystem and ecosystem functions, and that's very important information sources are needed to management decision. So together, previous issues are added by the understanding that the hydrology and actually the sediment transports are fastly changed, not only due to urban pressures, but also because of the, let's say, hydroclimatic development, if we would speak more in more wide perspective. And if we look on the reported in the literature values for these largest Russian rivers, we would see that's the trends in the sediment yields are rather huge for the last 30 or 40 years, and that's up to twice change in the sediment transport due to very different drivers are happening in the areas on the north of Russia in these largest rivers. And that's why we need to know, we need to have a new data on this new state of the rivers, but also in relation to the understanding of what is the sediment problem is from the perspective of our studies of pollution, there is very important thing that in Russia, we have the large river of Russia is the reference of natural state. And it's like a field lab for Arctic or subarctic rivers to learn about fluvial process and sediment transport. And this is the reference of natural state is incredibly important if we compare Russian conditions to, let's say, Western conditions, where the huge need to restore everywhere where this is possible a certain natural state of the river is important and is looking like a crucial step in the development of, let's say, water management in general. And that's why the examples and the detailed analysis of the rivers are crucially important. And to prove this statement, I would show this slide, which shows the two rivers in Poland. The largest river of Poland, Wisla River, which has been changed its channel due to artificial regulation during the all ancient, or not so ancient, historical periods of the development, and it's became from the braided channel, it's come to this rather heavily straightened regulated channel, whereas Russian rivers are usually looked like a very broad and very natural big areas of water flow without any, on the long reaches, without any either population at all, any settlements, or without any specific regulation works, which can be seen like some impacts on the river course. And so from this perspective, there is the needed to know these backgrounds or baseline conditions for the river systems, and this is the best area to learn about this baseline condition is these largest rivers of Russia. But if to summarize together what was said in the previous slides, I would again focus that even we are looking to the knowledge for the large Russian rivers, we are facing the big problem with the monitoring, which is not sufficient to provide enough data sets for the both hydrological issues, but especially for water quality or sediment issues. And then hence the scientists are looking for some surrogate techniques which can be used as some proxy to study, in our case, the sediments. And one of these approaches, quite useful and well known for different parts of hydrology, is the remote sensing. And on the next couple of slides, I would briefly describe how we can use the remote sensing to study this sediment flow and what is the application of this approach for the large rivers. So actually the whole, so just I will add my, so probably you have this on the slide. Yeah, so if we look on the some sort of the illustration of how their satellite images can give us information about their constituents in the water, we will see that the reflectance in different channels depends on and is based on the different possibilities of these channels to pass the water column, and based on the amount of material which is suspended, so dissolved in the river, the reflectance itself is changing. And then we're having the possibility to go from the so-called digital numbers of the reflectance to the exact values of the sediment concentrations. So, and in general, it is accepted that the amount of the sediments in the water column affects the reflectance or the image values, and then especially in the red and infrared channels, the relationships are rather significant. And based from these facts and quite broad literature on the topic, we are working on the general workflow of the Landsat image processing system, which can be based on the collection of the images which are also additionally studied in terms of the ground truthing. And the ground truthing in this way is the simultaneous measurements of the sediment concentration in the surface waters to build a relationship between the sediment concentration and these parameters of the image. So, and when we got this regression model, we can add the rather big collection of the images and from different years to come to the conversion of the suspended sediment concentration from the this relationship, which was done based on the ground truthing, and deliver this relationship to the whole collection of the images, and then to learn about the sediment transportation issues in the very long-term perspective and in the very spatial diverse manner. So the monitoring station would never provide you sufficient information for the large areas about their any kind of sediment properties, and the specific field surveys are very expensive, and sometimes it's not possible to operate with them, and hence the approach of the ground truthing give us a novel design for monitoring of the sediment transport in the big river system. But to confirm that we are on the right way, there is the need for several image processing options before the image can be used for the sediment studies. And here I would briefly comment the main steps of this image processing procedure. The first is the radiometric correction, which is done in a possible automatic way, which gives us the correction from raw values to reflection coefficient. So we come to rather unique relationship or unique parameters of the images when we are making the radiometric correction. The second thing is the atmospheric correction, and we are in a sort developed the technique which we call dark object. It's mean that we are looking for the water body on the image with constant brightness. It's mean that this should be pure water without any sediments, and in many cases the lakes without any tributaries, or the huge lakes like Baikal Lake, for example, which will be further in my talk mentioned a few times, is the best solution to make this, to apply this dark object technique. And then when we are taking with when we are working with the image where some sort of cloudy impacts can be observed in the atmosphere, we should make a correction, like in the example we got here. This is the clean atmosphere, and here the atmosphere with some cloudy stuff, and then we can need the correction of 0.2 for the reflectance coefficient, which means that we proceed to with the atmospheric correction. Then there is back to what I already mentioned. It's the necessity to have the regional relationship between the parameters of the sediments concentration and the image reflectance. So very briefly, I would just say that actually the hydrological waves on the large river system is typically rather broad, and I would use some of these results in their further examples in my lecture. But what we are really needed, so we can use the turbidity, which is fast procedure to measure quite large amount of the sediment concentration around, using the also relationship with the suspended sediment concentration for each water body. And then from these measurements, we can go to calibrate the reflectance coefficient and to come to the regional relationship with between the reflectance coefficient and the suspended sediment concentration. And actually the error, which is always the point in such kind of surrogate techniques, is rather important. And we provide enough statements and enough evidences that for different images of different resolution, there is the error up to 20% happens in the low sediment concentration values. And when we go to the higher levels of sedimentation, I mean larger suspended sediment transport, the error can be decreased, but we have the sort of the upper boundary condition for applicability of this method. And when we come to the sediment concentration upper than 500 milligram per liter, the relationship became not so strong, and actually at some moments we lose the signal on the image from the different turbidity or different sediment concentrations. So, but anyway, for typically 99% of the rivers, it's quite reasonable parameter to work with. But there came another point, that's the applicability of the remote sensing data is the function also of the river size. And this is the point which is described on this graph. So here we have the resolution of the images. And this is the minimal width, which we assume that this river can be used to study to study the sediment transport issue based on the remote sensing technique. So, and let's say empirically, we came to conclusion that the 3 pixel in the width of the river is enough to have a sort of the high level of the consistency in the remote sensing techniques. So, and then we can upload different, we plotted different remote sensing techniques to this graph to see from which sides of the river we can apply the different satellite images. And you see from the high resolution images, we slowly go to the large river, and the Landsat itself is starting from something like 90 meters applicability of the remote sensing. So, and here then we will talk about the areas which are larger than that. And like an example of what kind of data can be taken based on the these remote sensing techniques, there is the Selenga River on the example, which is flowing from the Lake Baikal, which is the not from the Lake Baikal to the Lake Baikal from Mongolia. And this is the river, the largest transboundary river of the border between Mongolia and Russia. And the red dots are the images which were of the good quality from the terms of the clouds and terms of the spatial scope to learn the sediment issues in the delta of the Selenga River. And you see that since the 1990 until the 2015, we have quite good distribution of the images, also which cover the extreme flow events and which cover the low flow events. So that's just of course, the ice cover period is not possible to study. And then there is their idea to work with the sediment bullets is coming. And so I would, as far as there's like half time of my presentation is flowing out. So I would switch to the case studies with the exact examples, what we can learn, what the scientists and their researchers can learn from application of these remote sensing techniques for the largest rivers. And I would start from the deltaic areas of the largest tributaries of Lake Baikal. There's two big deltas in the Baikal Lake. It's the Selenga River and the Upper Angara River. So the Lake Baikal, it's not maybe the big issue to talk about this largest freshwater pool of the world. And as the Upper Angara Delta is located on the top, on the north of the Baikal Lake, here it is, and on the southwest is the southeast is the Selenga Delta, which also is famous like biggest freshwater delta of the world, interior delta of the world. And for each of the deltas, we got this kind of mentioned before relationships. And then we are, after the calculations of the sediment budget along the main channels of the delta, and so we got 7 transects which cross the whole delta, and each transect was treated in terms of the difference between the sediment concentration on the output of the transects, for example, here, compared to the amount of sediments which are coming to the delta. And so the delta is quite large, is 500 square kilometers, which is quite big number. And so that's we came to such kind of the picture, which illustrates the seasonal variation of the sediment transport within these delta environments. And I would also say a few words why this is the issue of the research. The river brings a lot of pollution from their areas, also urban areas, and different mining activities, both in Mongolia and in Russia. And this is like a liver, the liver of the river system, which clean or named to clean the pollutants which are delivered to Lake Baikal. And the typical in there that's that in the area of Lake of the Delta, it's called that it's like a buffer area that's constantly decrease the sediment load. But the applicability of the remote sensing can give a new clues about how this system actually works. And so on this graph, you can see that this is the discharge, the water discharge on the top of the delta. And this is the balance between the sediment concentration on the budget on the output of the delta and then on the upper parts of the delta. And we found that on the low discharge, which is the left of the graph, we can have two possibilities of the changing along the whole system. In some cases, there is the longitudinal increase, which called like erosion. So the sediment concentration is increasing to the lake edge of the delta. And in some cases, there is also deposition happens in this during these low water periods. But when we go to the high discharges, to the floods, upper something like upper than 1,500 cubic meters per second, in these hydrological conditions, the sediments are blocked in the delta. And this is quite evident that the situation is changed a lot. And then there is a question, low water, we have quite higher values of the sediment budget. So it means that there is also longitudinal increase sometimes happens. But in the high water period, there is always decline of the sediments which are washed into the delta. And the quite evident answer is the sediment rotation during high water. So if we look on different hydrological pathways of the water in the such kinds of the flats environment, we will see that there are a lot of water during the high flood events go to the banks, flood the areas, the roughness is increasing, and we come to have a lot of different blockages in the system, which are associated with these high level discharges. So this is on the graph. You can easily see that there is the wetlands itself became much more effective in terms of the impacts of the influence on the river system. And there is different sorts of these blockages are happening. So the first is some bogs, the second is the lakes, and the third is just the flooding of the surface of the floodplain surface. And in terms of the just pictures, this is what we usually know. In terms of the how the system works in general, so this kind of statistical data is something, let's say, new for scientists to see the seasonal formation of the sediment budget. And there can be other factors also discussed. And firstly, this I'm talking about the possible impacts of the Baikal level fluctuations. And here on the graph, you can see the red is the discharge and the blue is Baikal level. And so we see that for especially low water conditions, when the Baikal level can be associated with rather high levels, and we have the blockage, the backwater effects in the downstream parts of the delta, which can be the reason of the also the stop of the flood delivery into the lake. But vice versa, there is also another point. It is the surges, so the winds which coming from the lake, in which can also affect the secondary transport of the sediments which were previously deposited on the bottom. So, but anyway, the backwater effects from Lake Baikal should be considered. So I will skip this last slide of the previous case study and go to the third case study of my presentation, which is on a branching channel of Lena River. And this is, we go to the north actually in the list of the case studies. And this is the sort of what I have shown in the very beginning, these huge and branching areas of the natural Russian rivers, where sporadically some settlements are located, but you can fly over the Russian territory for a few hours and you would see no settlements and no roads, only forest, taiga, and you will cross many such kind of rivers. So it's the huge environment, but it's incredibly interesting in terms of how the suspended loads is transported here. And based on the similar sort of application of the remote sensing techniques, we discovered that there is actually the whole variability of the sediment transport can be described by three main patterns. So the first is the depositional, which also happens during high water. So we here, I would just run forward, but we here also conclude the seasonality in the sedimentation system. So the depositional during the high water events and so-called erosional, it means that we have the longitudinal increase of the sediment transport during the low water. And also the transverse gradients, which are very important in this branching system, sometimes can prevail over the other drivers of the sedimentation. So there is the example of what is the critical issues of the how the flood propagations occur in terms of the sediment patterns. The first thing that when we got some reach without tributaries, and the length of this reach on the graph is 150 kilometers, almost what is on the left picture of the slide, we will see that when we go from the upper part to the downstream part, and when the river flow cross the big braided patterns of the island vegetated areas, there is the constant decrease of the sediment concentration in the mainstream. So the reasons for that is the same like with the delta area. So the more water is flooded on the surface of the floodplains, the roughness is increasing, and the sediment is captured on the floodplain lakes. And the empirical evidences of that on the largest rivers is the huge layers of the silt after the floods, which go through the floodplains. But another thing which is also important, which is, let's say, just observed, can be observed only via such kind of application, is the big difference between the floodplain branches, small side areas of the water flow compared to the main channel. So the differences in the terms of sediment concentration is huge. There is twice difference of the sediment passing these rivers. And I will be back to this explanation later, this quite nice hydraulic explanation. And we have opposite situation during the low water period, when we have increase of the sediments concentration along the river, and that's the focus and the answer. What's the reason for that is also the possible side effects of the bank erosion or the erosion of the bottom, and we are aware of that the reefs are eroded during the low water period. So, but it is quite also typical to see the increase of the on the downstream increase of the sediment concentration, and then we can see that's very nice picture of the same reach for the high water period and the low water period, and you can see on the same area. This is the, if you are familiar with Lena River, this is the reach from the city of Pokrovsk. Here's the Yakutsk, and here's the mouth of the Aldan. Straight after the picture is on the north is ended up. And so on the high water period, there is the constant decline of the sediments in this reach, and on the low water period, we have constant increase of the sediments in the system. And this is also can be proven statistically. That's the sediment budgets under different discharges has the different intervals. And the sediment budget here is again the difference between the average sediment concentration on the lower part compared to the upper part of the reach. So, and this is the discharge. So you see that's the larger discharge, the lower sediment budget, meaning that we are slowly going from the erosional system to the depositional pattern. And there is the hydraulic explanation for that. We simply compared the high resolution grids of the flow velocities with the sediment concentration, and rather suddenly we came to rather significant correlation between the velocity, surface velocity, and even bottom velocity with the suspended sediment concentration for the low water season. And then if we count the transport capacity, we will also got the rather significant relationship between the sediment concentration and this transport capacity. So, and the number of points is not the issue to be unaware of the quality of results. So each point on the graph, on the previous graph, is thousands of the grid cells, because there was the huge grid cells which was layered one to another one with the one is the sediment concentration, the second is velocity. And each box here is something like thousands of the points. So, and that means that it's quite significantly significant relationship with the increase of the suspended sediment concentration compared to surface velocities. And the third pattern is these transfer gradients. And this is a specific issue which is also sometimes very typical to the large rivers, and which I've been showing in the beginning with nice so-called wedging of the rivers. And this is the downstream area of the Lena of the same reach, but below the confluence of Lena and Aldan. And there is a very typical picture which can be observed from satellite when there is the two water flows of different suspended loads are formed, and which can be mixed or can be going in rather large, long directions. This is 200 kilometers length reach again, and this is the Veluri who is coming and without any mixing. But if we try to count and we split geometrically split the river channel in the middle of this ridge, just simply based on the width, and then we count the sediment concentration in this part and on that part, and then we will come to significant relationship, not significant relationship, but we will have the evidence that the sediments relation, the ratio between the sediments in the left part of the channel and in the right part of the channel is the function of the water discharge in both areas, in both rivers. So, and I would say that it is the end for the discussion about the second case study, which was focused in my presentation. And very briefly, I would say a few words about the third one, about the system which is not so well fits the previous results. So, and this we are going to the top of the Siberia, and we're coming to the another huge delta, the second delta of the world. The first is Amazon, the second is the Lena River Delta, and this is the area of the big permafrost system and distribution. And the word permafrost is very important for us here, because permafrost explain us that hydrologically the sediment transport issues work in very different manner compared to the both Lena on a branching channel, which we talked about before, and compared to the deltas of the tributaries of Baikal Lake. So what does it mean? So it means that if we look on the imagery, we will see the very complicated system with impacts on the sediment transport from different sources, both like the coastal erosion, the bank erosion, and the deposition in the flooded lakes. And if we try to make the similar approach to count the sediment budget as a function of the water discharge for the Lena Delta, we would see quite sporadic picture without any real clues that any evidences that there is some sort of relationship. And so the erosion and deposition can happen both in the at the floods, at the low discharges, and that's quite. We see that it's another story. It's not fits the previous case studies. And then if we go in more details and try to look what can be the reason for that, we found that elsewhere, when we have the summer days on this right part of the Lena Delta, this is Bykovska branch, we will, on many areas, we will note the increase of the sediment concentration under the exactly left bank. And then that's based on the literature and based on the what we see in the area, we found that this area, this bank, exactly this left bank, is located on the ridge of the river, which is flowing from the west to the east. So it's meant that it's northern bank of the river. And we have the increase of the sediment concentration. What does it mean? It means that this is the permafrost thaw here. The thaw of the permafrost bring a huge amount of the melt water with the sediments, with the clay and with the silt in the river system. And this became the main driver of the whole evolution of the sediment budget in the Delta of Lena. And this brings us to the idea to try to combine this sediment budget with the air temperature. And we see that there is some relationships between the air temperature and the sediment budget. And it means that the hypothesis of the impacts of the thawing permafrost on the sediment budget is, in this area, is working. It's the possible phenomena which explain the whole formation and transport of the sediments to the ocean. And then we came to the understanding that the new environmental drivers became crucially important. And even compared to the urban sediments, in these scales, the changing environment, the hydroclimatic developments of the area is the huge stressor for sediment budget. And then we come to the pictures that give us some examples of how the sediments go through the system. And on this slide, I would come to the conclusion, considering the time of the lecture. And I would firstly say that few positive words about the generally the applicability of the remote sensing techniques to study the issues related to sediments problems, and this is also compared to the issues of the in some way of the related to the quality of sediments. And there is few techniques which are valuable to work with the sediment quality in this regard. And then the seasonality is the key feature of the functioning of the large river system is important, and it can be simply hydrological, which is worked with the or is the function of the floods and the low water seasons, or it can be that the function of the more complicated environments like the related to permafrost soil. And of course, these issues provide us with the understanding that the high spatial variability of sediment transport rates between small and large channels in the such kind of braid system is very important. And this further is a bridge to the monitoring strategy and to the big application in ecology. And before I finish, so we are still inviting all of international participants to our conference, which was shifted to then from 2020, like on the slide, to 2021. And we are planning, hopefully, to organize it like normal conference or hybrid conference. Anyway, you are very welcome to register. And I put this slide when I was looking on the last slide of the previous speaker, for my good friend Bjorn Helm. And actually, I put here the urban hydrology issue from Moscow. It's yesterday in Moscow we measured discharge in this, let's say, very dirty rivers with the huge amount of sediments. And compared to the atmosphere, which is also my good friend Mikhail Samokhin. And on the left slide, there is another picture from this summer from the Kolyma River, which is a completely different story compared to these Moscow environments. And it's very, in terms of the sediment and water quality, clean river. And the beer is the thing in the hands of my another friend, Dr. Moreida, is the thing which also confirmed that this is the very different areas to study, but both of them are very challenging in terms of the applications. Thank you very much.
Thank you very much, Sergey. Very interesting presentation. Very new from poorly known areas. So there are a number of questions, and some of them are here. So first, there is not a question, but Mr. Abir Ben Slimanes, thanks you for the presentation and the interesting subject. And then is the question from student of hydrology department, Moscow State University, Viktor Lomov. The question is it possible to use drones instead of Landsat for the same goals, and maybe it will be more accurate than satellites measuring?
Okay, so thank you for firstly thank you for convener to lead the session. Thank you for nice feedbacks in this question list. And regarding the question itself, I would say that the drones is applied, and it's not the matter of accuracy in terms of the application of the drones. It's the matter of the scaling and of the other, let's say, resolution of the rivers to apply. So based on the drone technology, we are able to apply or to study rather small rivers with the similar issues of the sediment transport problems. And this, I would say, the first possibility which brings out the drone itself. Then another point can be the studies of the maybe another physical processes like a turbulence based on the drone technology and the impacts of the turbulence on the sediment transport. It's quite challenging, new, and there are another story. Yes, thank you.
Thank you. The next remark is from Yossi Wilson. Great thanks to Dr. Chell for an interesting presentation. And the question is to use GIS for the treatment of obtained data and to state further research. Do you use GIS? Of course.
So actually, that's the application of what we use regular is the general ArcGIS software, and let's say the main results which I showed in the presentation were done in normal in normal toolboxes of ArcGIS. So we didn't use any specific usually software for imagery. So it's not sometimes the good point, but it's then more relevant to combine our studies with another applications. And when we are working on the interface between hydraulic and this remote sensing applicability, then it's the GIS and like normal SRI products is very useful. So anyway, thanks.
Okay, then what is statistically significant of the relationship between turbidity by satellites and in situ measurements? The Pearson are sometimes is not enough information for such relationship. What can you answer? What is statistically significant?
So it's yeah. In general, we use the correlation coefficient, and we assume that more than 0.7 is statistically significant. So we are not making some very, let's say, rough calculations. So, but we based on this quite traditional criteria. This is the first thing, and the second that we are not only focusing on pure statistics, we will also worked with comparison between the images and the on situ data with the independent, let's say, independent observation, which were not used for the imagery, for the processing of the relationship. And on the graph in the first part of my presentation, there was the numbers of the errors, which were up to 20%. And these errors were assumed based on this, what I called, let's say, verification. So we didn't make any, we didn't use for the error estimation this sort of statistics. We just simply compared the observations with the image based on the recalculated, based on the relationship which was taken from another field campaign. And this is a normal procedure, which I would say is just independent of what you are asking. So then I guess I answer a question in this regard.
Thank you. One more question from Dr. Pankai. How close estimates to the observed date of sediment? How close estimates?
How close estimates?
Yeah.
Actually, that's maybe I already answered this question. So the difference is up to 20% in the when we have the sediment concentration below 100 milligram per liter. So it means that we can have an error in sort of the 10 to 15 milligram per liters, which in some way can be large, but this is the error which is stochastic error, but it can be assumed like a large. But then if we talk about the errors and the correctness of the monitoring and the other typical traditional forms of the measurements in hydrology, so this is quite normal value, which is not bad for such kind of the studies.
Thank you. And two final feedbacks, I would say. From first from Zara Abdullahi, would you mind to put your contact information?
We will announce on with the lectures those of the speakers who will agree with the to share the contact information. We will copy the recorded videos to the YouTube channel with the contact information. So I guess from my side it's okay. So we'll ask all the other speakers as well.
Okay, and the general, I think, feedback from all of the listeners, it is by Paulina Adamiak. Thank you very much, Dr. Chalov.
Thank you.
Sorry, just a moment. We have 3 minutes, so 2 more questions. I see one is from Miguel Ignacio Barrios. Thank you for your presentation, Dr. Chalov. What kind of regressions could be reliable for these applications? Classical models, machine learning?
So we used classical models. We never used for this kind of application anything else, and we used linear regression. And we played with different other possible options, but the linear regressions as the classical sort of the statistics works better in all cases. So probably, of course, that many things can be done in sort of the developing the technique of building the relationship, but yes, we use classical methods.
One interesting question from Mr. Pankai Kumar. Excellent study. I have a query how to take bed load proportion from satellite image.
There is
proportion from satellite image.
So that's not actually the straight procedure. So we never did anything with the bed load techniques. But if to speculate a little bit, then if we count suspended loads, we can use a regional relationship between the suspended load and the bed loads, and then we can actually build some sort of the rock flow to count also to speculate about the bed loads. So, but of course, it's not the study what I was talking about. It's something else. It should be developed also theoretically.
Mm-hmm. So, and the final one from Suvin Duroy, and the question is, can we use your constant values regarding the relationship between reflection value and SSC in other rivers in tropical country?
So I would say like that, there is some application of the similar technique which can be found in the literature. And I would say that on Friday, we will have a talk of Dr. Ladbruse from Brazil. And he's the one who published very nice paper on terms of for Amazonka catchment about the applicability of the similar approaches. So I think that each river requires the specific regional relationship. And for the tropical rivers, it should be treated specifically. Of course, it's not the method just to take the relationship and to bring it to another river system.
Okay, and so the very last question from Dr. Muchanga from University of Zambia. Are you open to collaborative research on sediment studies? Are you open and collaborative research on sediment studies?
We are always open. Russians are very open in different ways, also for research, for friendship, and for everything. Welcome to Russia.
Thank you very much, Sergey, and thanks to everybody taking part in this session.
Okay.
Goodbye.
Thank you. Goodbye.